All right, guys, welcome to this page of the notes. Now, what we just did was we just talked about the remainder theorem, which says that if I do synthetic division, the remainder, what's left over after I do the division, is exactly the same thing I would get if I had done substitution. Right? So we're going to use this synthetic substitution, what we call synthetic substitution, to evaluate a polynomial. Here we go. This is the way it's going to work. I have given you a polynomial. I have asked you to use x minus 4. And so remember, to set up synthetic substitution, you have to set x minus 4 equal to 0 and solve. So I'm going to do my synthetic division with a positive 4. Check to make sure you don't need any placeholders. 4, 3. I am missing somebody, so I'm going to have 3x to the 4th minus 2x cubed plus 0x squared plus 5x plus 2. Right? I need that placeholder for that missing power of x, and now I'm all set to set up my synthetic substitution, or my synthetic division. The 4 goes inside the box, and now I pull out all of those coefficients. 3, minus 2, 0, 5, and 2. Use the bar to separate my work from my final answers. And here we go. Drop down that 3. 4 times 3 is 12. Add them up. That's going to be a 10. That's 40. 40. 4 times, let's see, 4 times 40 should be 1. What do I get? 160. Add them up. That's 165. 4 times 165 is 660. And I wind up adding those guys together, 662. Okay, so this guy right here, right, this last number is always going to be your remainder. And so here's what we've just done. If you had done f of 4, which means 3 times 4 to the 4th minus 2 times 4 to the 3rd plus 5 times 4 plus 2. If I had done substitution, where I plugged the domain value of 4 into the polynomial everywhere I had a variable, plug this into your calculator and hit enter, you would have gotten f of 4 is equal to 662. All right, what we're using is this method of synthetic substitution, where I do synthetic division, and the remainder is the value I would have gotten if I had evaluated the function, right? So when I ask you to use the remainder theorem to find the value of the function by substitution, that's it. 662 is your answer. That is what you would get if you had evaluated the function, the polynomial, at 4. Let's do another one. I give you a polynomial. I ask you to use x minus 3. So again, to get this guy set up, x minus 3 is equal to 0, which means x is equal to 3. Make sure I have everybody 3, 2, 1, 0. Everybody's there. I don't need any placeholders. So we set this guy up. 3 goes inside the box. 3 minus 6, 1, and negative 11. Bring the 3 down. And here we go. 3 times 3 is 9. That's going to leave me with a positive 3, which again is 9, which is going to be 10. Which is going to be 30, which leaves me with 19. Now again, the remainder is the answer I'm looking for. What this means, 19 is the answer. It's the value I would get if I plugged a 3 into this domain value of 3, into the polynomial everywhere I had an x. So f of 3, if you did this on your calculator, you're going to get 19, right? That's what you would get, right? This remainder is the answer you would get if you evaluate the polynomial at 3, all right? So I got a couple more example problems for you. Let's try these ones. Here we go. Again, we're going to use synthetic substitution, so I need to figure out what I'm going to do my synthetic substitution with. X plus 1 is equal to 0, which means x is equal to a minus 1. Check to make sure that I don't need any placeholders. 5. I absolutely am going to need a couple of placeholders, so let's go ahead and get those placeholders in there. I'm going to have 4x to the 5th plus 0x to the 4th plus 2x cubed plus x squared plus 0x minus 1. So there we go. 5, 4, 3, 2, 1, 0. All of my powers are represented, and I needed to use two placeholders. Let's set up our synthetic division. 4, 0, 2, 1, 0, negative 1. And here we go. All right, I bring down the 4, and then it's multiply, add until I run out of numbers. Negative 1 times 4, it's going to be a minus 4. Add them up, minus 4. That's going to give me a positive 4. 4, 5, 6. That's going to be a negative 6. That gives me a minus 5. It's going to be a positive 5. 5. That's going to be a negative 5, which means I wind up with a minus 6. Okay, so here's what I get. My remainder after doing synthetic division is a minus 6. And again, remember what that means. If I were to substitute this domain value, negative 1, into my polynomial everywhere I have an x, what I would get when I evaluate the polynomial at negative 1, I would get a minus 6, right? That's the answer I would get out. So we did synthetic substitution using what's known as the remainder theorem. The remainder theorem tells me that the remainder is exactly the same value I would get if I had done substitution for this domain value into the polynomial. All right, now, I told you guys, you're probably thinking to yourself, why would I go through the process of doing synthetic substitution when I can just plug that value into, plug that domain value into the polynomial and just simply evaluate? Like, why? What's the point? Here's the point. We're going to do this example problem, and what you're going to see is we're going to get a really interesting remainder here that's actually really, really important. So let's go ahead and do this one. X plus 3 is equal to 0, which means x is equal to minus 3. So I'm going to use the domain value of minus 3. Check to make sure I don't need any placeholders. 3, 2, 1, 0. Everybody's there. Go ahead and set up your synthetic division. So minus 3 goes inside the box. 2, minus 3, negative 17, and 30. Bring down the 2, and away we go. Multiply and add till you run out of stuff. Negative 3 times 2, minus 6. Add them up, negative 9. That's going to be 27, which means what's left over is a positive 10. Negative 3 times 10 is a minus 30. And here's why this problem is so interesting. I add those guys together and I get a remainder of 0. This is my remainder. Now, remember what a remainder of 0 means. When you get 0 as a remainder, that means that this polynomial is evenly divisible by the quantity x plus 3. This is really, really important because what it tells me is that x plus 3 is a factor of the polynomial f of x equal to 2x cubed minus 3x squared minus 17x plus 30, right? This polynomial right here, the polynomial that I gave you, it turns out x minus 3 is one of this polynomial's factors. And you know that because you got a remainder of 0. They're evenly divisible by one another. And when that happens, you have a factor. Now here's why that is so important. In the previous section, back in section 5, back in section 6, section 5, we looked at several factoring methods to help us find the zeros of a polynomial, right? Factoring methods. You're given a polynomial and we want you to factor that polynomial so you can find the zeros. Well, look at what we just did. By doing synthetic division and finding a remainder of 0, I have just found a factor of this polynomial. So what we're now going to do, the second objective or learning target here in this section, is to use this idea, all right, that we can do synthetic division, and if I get a remainder of 0, I have just found a factor of the polynomial to help us get another method, for factoring polynomials and finding the zeros or the x-intercepts of that polynomial. I know this is epic stuff. I'm so glad we're taking this journey together. Head on over to the next page of the notes and I'll show you exactly how this is going to work as a method for factoring polynomials. I'll meet you guys over there.